Okay, uh, good morning, everyone. Welcome to the this Sea Level Rise seminar. We're very glad to have Emily Glazer, who is a PhD candidate in the Department of Earth and Environmental Sciences and the Lamont Polar Geophysics Group at Columbia University. And she is studying ice shelf stability using remote sensing and modeling, and her research interests also include glacier surface hydrology and mass balance of Antarctic ice sheets. Prior to beginning her PhD, Emily spent 2 years working on quantum technologies at HRL Laboratories, and she received her BA in physics from UC Berkeley. Today, she will be speaking on the topic impacts of temperature and stress-dependent rheology on ice shelf front bending. Welcome.
Cool. Hi, everyone. Thank you so much for being here, and thank you to Patrick for that introduction and for inviting me to talk. So, as Patrick said, my name is Emily Glazer, and I'm a PhD student at Columbia and Lamont-Doherty, working with Roger Buck. And I'm excited to talk to you all today about the impacts of temperature and stress-dependent rheology on ice shelf front bending. So first we need to ask, why do we care about bending at ice shelf fronts? So we know that there's huge uncertainty in how quickly sea level will continue to rise in a warming climate, as shown in this figure from the NOAA Sea Level Rise Report. Much of this uncertainty arises from the many complex processes that govern ice mass loss from the two polar ice sheets, Antarctica and Greenland. So some of these processes are represented here in the schematic showing the Thwaites Glacier in West Antarctica. About 75% of the Antarctic ice sheet is surrounded by floating ice shelves, such as the one depicted here. So grounded ice flows from the continent across the grounding line and terminates in these floating ice shelves, which can lose mass to basal melt, induced by warm ocean waters, or by rifting and calving, which can be induced by hydrofracture or bending stresses. So ice shelves play a really important role in mitigating sea level rise because of the buttressing forces or backstress that they apply against inland grounded ice as they run aground on local topographic highs or pinning points, or shear against lateral confinements or slower moving ice. So these are particularly complex and important regions to study because they interact with both the atmosphere and the ocean. Today we're going to talk about ice shelf bending at the ice front, and studying this region can give us a better understanding of the stresses that can lead to fracture and to rifting. And then furthermore, we're going to link our study of ice front bending to the more general idea of ice flow. So we know that ice deforms as a viscoelastic fluid, but the parameters describing the viscosity are very poorly constrained, which is a major cause of uncertainty in predicting ice loss. So our study of bending provides a means to help constrain these parameters, which I'm going to be discussing throughout this talk. So now, if we consider an idealized rectangular uniform rheology ice shelf, we expect the competing stresses at the front to lead to downward bending. To go through the math here, we can calculate the total bending moment of the ice shelf front as the sum of the integrals of the competing forces due to the longitudinal stress, sigma xx, pushing outwards, and the hydrostatic water pressure, P sub W, pushing inwards. The water pressure increases linearly with depth, starting from the freeboard height, as indicated by the orange arrows. And the longitudinal stress is equal to the ice overburden pressure, sigma zz, minus a constant driving stress difference, delta sigma. The overburden pressure increases linearly with depth from the surface, and the stress difference can be computed simply using horizontal force balance. So when we plug in all of these variables, we can derive this expression for the total bending moment. Note that this bending moment is negative, indicating that we expect an idealized ice shelf front to bend downwards. However, there are many observed instances of upward bending at ice shelf fronts. So this cartoon from Becker et al. 2021 shows an ice shelf that bends upwards at the front, terminating in what we call a moat rampart structure. So the elevated edge is called the rampart, and the surface depression is called the moat. These structures can have bending amplitudes, defined as the elevation difference between moat and rampart, of up to 20 meters, and they bend upward with a short wavelength of a couple hundred meters. So these moat rampart structures are found at several ice shelf fronts around Antarctica, and they actually comprise about 75% of the Ross ice shelf front. So Ross is the biggest ice shelf in Antarctica, and it's shown here in this, or its front is shown here in the shaded relief map, also from Becker et al. So we can see that the front spans about 800 kilometers, and the red shading along the front indicates the upward bending amplitude. So there's moat rampart structures all across the front of the ice shelf, with the largest amplitudes up to about 20 meters on the West Antarctic side. So this, of course, begs the question of what is leading to this upward bending. To answer this, let's start by looking at some ICESat-2 lidar data from shelf fronts around Antarctica. The top figure is from the Amory Ice Shelf in East Antarctica. The photon data shows us that the surface bends downwards at the front, terminating in a more classic berm profile. This is what we expect from ice with relatively uniform viscosity. The Shackleton Ice Shelf, a warmer ice shelf also in East Antarctica, shows upward bending at the front with this subtle moat rampart structure. And then we can also see evidence in the photon data of a submerged ice bench underneath the sea surface. This is evidence of a widely studied mechanism for upward shelf front deflection. The idea here is that warm, near-surface ocean waters will erode away at the ice front near the surface, causing a small chunk of the ice to break off. This missing ice results in a buoyant force at the shelf front and consequent uplift. However, there's no evidence of an ice bench that's been spotted anywhere along the Ross ice shelf front, even though we see clear upward bending in much of this region. And here's just an example of a photon track from the Ross ice shelf front. We can see this clear moat rampart structure. So this brings us to our novel mechanism to explain upward bending, which is that strong vertical variations in ice viscosity can lead to upward bending even in the absence of an ice bench. So ice shelves are generally warmer at the base than at the surface, and ice viscosity is temperature dependent. Therefore, this viscosity gradient can induce an internal bending moment. If the bending moment is large enough to overcome the negative bending moment from the seawater, we expect a net positive bending moment and consequent uplift. So to corroborate this idea of the importance of viscosity variations, we can go all the way back to 1968 and look at this paper by Niels Rhe, which was a pioneering analysis of shelf front stresses and bending. So in this paper from almost 60 years ago, Rhe states that a correct treatment of the problem would require consideration of the great variation by a factor of 10 or more of the viscosity. This, however, would involve enormous mathematical troubles. So rederive the bending moment, just as we just did a couple slides ago, assuming constant viscosity. However, he states that the result can therefore not be expected to agree with nature. So now we can return to these mathematical troubles that Rhe identified. Starting, of course, with Glen's flow law, which describes the nonlinear relationship between viscous strain rate, epsilon dot, and driving stress, sigma. The nonlinearity is defined by the flow law exponent, n. We incorporate temperature dependence into the flow law via the Arrhenius dependence of ice softness on temperature, which shows how the ice softness parameter A varies exponentially with the ratio of the activation energy of melting ice, Q, to the ice temperature, T. We can rearrange this equation to solve for the driving stress, delta sigma, as a function of temperature and a constant strain rate. And now, throughout this work, we assume a linear temperature profile in which the coldest temperature is at the ice shelf surface, and it increases towards the base with a constant gradient. This allows us to express the driving stress like this, and if we make the approximation that the temperature difference is small relative to the absolute temperature, we can do a first-order Taylor expansion within the exponential to derive a driving stress that simply decreases exponentially with depth, as a function of this e-folding distance z naught, which depends on the ratio of the activation energy to the flow law exponent, Q over N, as well as the temperature gradient, the difference between the surface and base temperature of the ice shelf. So now back to our expression for the total bending moment. Now that we have depth variable rheology, the driving stress is no longer constant with depth, but rather decreases exponentially, resulting in the following expression for the total bending moment, which depends on Z0 star, or the thickness normalized E folding depth. So this figure represents this big ugly equation. It represents the total bending moment in this parameter space, represented by surface temperature of the ice shelf on the x-axis and the ratio of Q over N on the y-axis. These parameters dictate the bending moment, assuming that we're always using a base temperature of 0 degrees Celsius. So we can see that for sufficiently high Q over N, indicating a strong dependence of viscosity on temperature, and a sufficiently low surface temperature, we expect strong vertical variation in viscosity and consequent positive bending moment and upward bending at the shelf front. Otherwise, with weak vertical variations in viscosity, we expect a negative moment in downward bending. So this analytic model predicts upward bending for cold surface temperatures and a range of ice rheologies. However, it relies on the thin plate approximation and requires use of an arbitrarily chosen flexural wavelength in order to actually predict the resultant deflection amplitude or geometry. So in this study, we employ a two-dimensional viscoelastic model in order to test these analytic predictions, to show how the flexural wavelength and the edge deflection evolve over time, as well as to compare the bench and moment models with observed Moe rampart geometries. So to test these predictions, we ran two-dimensional numerical models of ice shelf fronts bending over time. We modified a fully two-dimensional explicit finite element code base called FLAC, and we used a rectangular floating model domain fixed on the right-hand side and with hydrostatic boundary conditions on the left-hand side and the base. Our models all used a Maxwell viscoelastic rheology. And then we ran these models with a variety of rheologic parameters. We've varied the ice thickness, the activation energy, the flow law exponent, and the average viscosity between model runs. So now to our first goal, which is to test the analytic predictions of ice shelf front bending. Here we're looking at an animation showing the evolution of two modeled surface profiles over the course of 5 years. The red line on the left and the top plot on the right represent a warm surface, uniform temperature ice shelf with relatively uniform deviatoric stresses. The blue line and the bottom plot on the right represent a cold surface ice shelf with depth-varying temperature and deviatoric stress. So note that as expected from the analytic solution, the uniform ice shelf bends downwards over time, and the cold ice shelf bends upwards. The dashed lines on the surface plot represent the thin plate analytic prediction for the surface profile as a function of the moment and the modeled bending wavelength. So note that the directionality of the bending matches the analytic predictions in both cases. However, the model shows higher magnitude bending amplitudes. And we found that this is due to two-dimensional effects that arise when we examine the full depth shape of the modeled ice front instead of just the surface. So we'll look at that now. So this animation shows the evolution of the full depth ice shelf fronts for 4 of our model runs over time, in which we were varying the activation energy. So you'll see that the ice shelves are expanding laterally over time. This is expected as the entire ice shelf is spreading out away from the continent as it viscously deforms. So note that while the shelf fronts start out as rectangular, the bottom of the shelf front starts to bulge out ahead of the top. In the high Q case, shown in turquoise here, we see a difference of almost 20 meters between the top and the base. So this is because while the ice shelf strain rates even out at far fields, at the shelf front, we expect the strain rate to be dictated by the depth variable viscosity. So this leads to the bottom, less viscous portion of the ice to protrude outward beyond the colder ice at the surface. So these lateral flow variations with depth cause a bulge pattern at the shelf front that increases over time. You'll notice that the frontal bulge creates a geometry very similar to the submerged ice bench, which results in additional uplift. So just like the ice bench, the bulge pattern creates a buoyant load due to the non-rectangular shelf front geometry. Thin plate theory suggests that edge deflection due to a buoyant load increases linearly with that load, V naught. And in the case of a frontal bulge, the magnitude of the buoyant load is equal to the density difference between ice and water times the gravitational acceleration times the area of the bulge, which I've represented on the schematic here. So here we can look at the approximate edge deflection, which can be attributed to the bulge for a few of our upward bending models. So this first plot is again showing the full depth ice shelf front shapes after 5 years. And the middle plot shows the edge deflection due to the bulge over time for each model. So the uplift from the bulge increases linearly with time as the bulge area increases. And the uplift due just to this effect is up to about 3 meters for the high Q case. And the plot on the right represents the percentage of the total uplift that can be attributed to this effect. We see that the bulge could account for as much as 30% of the modeled uplift, which could explain why our model results outpace predictions. And now our second goal, which is to show how the edge deflection and the flexural wavelength evolve over time. Our thin plate approximations for elastic and viscous bending wavelengths are shown here. The elastic bending wavelength is a textbook result depending on material properties. The viscous bending wavelength is derived by Olive et al. 2016 and shows that we expect the wavelength to decrease over time with t to the minus 1/4. We can combine these equations to derive an expression for the viscoelastic bending wavelength, which is a function of what we have termed the effective layer Maxwell time, T0. Plugging this into the expression for edge deflection due to an internal moment suggests that the uplift should increase with time to the 1/2. This animation represents the temporal evolution of an upward bending model run, with the colors from red to blue representing model outputs of the surface geometry every 3 months for 5 years. We can see that the bending wavelength gets smaller over time as the deflection amplitude grows, and this was true for all of our models. This matches what we expect from the thin plate viscoelastic approximations. And we've also represented this here in this figure showing the relationship between edge deflection and wavelength for several of our model runs. So the y-axis HMR is the moat rampart height, defined as the elevation difference between the moat and the rampart, and the x-axis XMR is the horizontal distance between the moat and the rampart. So as the system evolves, the magnitude of the moat rampart height increases as the length scale decreases, with the direction of progression indicated by the black arrow. So note that all of the models show an inverse square relationship between deflection and wavelength, as expected, and that all of the models which have the same predicted bending moment, which we know if they have the same thickness and the same Q over N value, are on this same trajectory, have the same relationship between deflection and wavelength. When we normalize the deflection by the analytic bending moments, all of the models collapse to the same trajectory, as seen here in this plot on the right. The black dashed line represents the analytic prediction for the inverse square relationship between normalized bending moment and wavelength. So note that as expected because of the two-dimensional effects, the model deflections increasingly outpace these predictions over time. And now to our third goal. Sorry, one sec. Now to our third goal, which was to compare bench and moment mechanisms to observe surface geometries. So here we're looking at 2 modeled surface profiles, one showing upward bending from an internal moment in blue, and the other showing upward bending from a submerged ice bench, shown in orange. So both of these models were run until they reached the same deflection amplitude of about 5 meters. So we can see that the moment model produces uplift with a smaller wavelength and a greater moat depth than the bench model. This matches what we would expect from the analytics, which are indicated by the dashed lines. And now we can leverage these differences to discern between mechanisms observed in the ISAT-2 data. But before we dive into this comparison with data, I want to briefly motivate why this is important in the context of sea level rise. So comparing our model results with data can both help us constrain the mechanism of uplift and identify the rheology parameters that seem most realistic. So identifying the mechanism of uplift by looking at the relationship between uplift and wavelength can give us a better idea of the ice shelf stresses, which can help inform our predictions of future rifting and calving events. To exemplify this, we can look at the two-dimensional longitudinal devious toric stress distributions from the moment and bench model examples. The variable viscosity ice, which bends upward due to an internal moment, has the most extensional stresses near the surface, where the ice is the most viscous. However, the ice bending upward due to a submerged ice bench has relatively uniform stresses with depth at far field. However, there is an area of concentrated extensional stress at the ice base within a few hundred meters of the ice front. The location of maximum stress can be used to predict the location of rifting and calving, and has been codified in a study by Wagner et al. 2014. So this is just an example to show us how differentiating between mechanisms can help us better understand ice shelf rifting and breakup moving forward. And furthermore, comparing models with data gives us a means to constrain model parameters and therefore ice rheology. These model parameters include Q, the activation energy, A naught, the ice softness prefactor, and N, the flow law exponent. So recall Glen's flow law, which expresses the viscous rate of deformation, epsilon dot, as a function of all of these parameters. So it seems simple enough, but all of these parameters vary in complex ways on stress and temperature of the ice, and are poorly constrained and vary widely in lab experiments and field measurements. So the activation energy Q of melting ice describes the temperature dependence of viscosity. But ice softness responds more strongly to warming near the melting point, where the temperature is greater than about -14 degrees Celsius due to pre-melt effects. So because of this, Q is often represented as piecewise with temperature, with a higher value for warm ice than cold ice. Values for cold ice in literature and models range from 42 to 85 kilojoules per mole, and for warm ice from about 120 to 200 kilojoules per mole. The ice softness, A naught, dictates the viscosity for a given driving stress and temperature, and it depends on several properties, including water content and grain size. And the flow law exponent N describes the nonlinear response of deformation to stress. So the most commonly used value for ice is N equals 3, but literature and models show N varying from 1.8 to 4.5, with higher values corresponding with faster ice flow, less sliding, and larger grain size, corresponding with different deformation mechanisms. So to emphasize the importance of constraining these parameters, I want to show this figure from Zietz et al. 2020. So this study examined a simple ice sheet model in which the ice was sitting on a large flat continent as shown in the schematic on the left. Zietz tested the sensitivity of ice flow to different rheologic parameters. The plots here show what happens to the flow-driven ice mass loss after 100 years of 2 degrees Celsius of warming. So the y-axis shows the ice loss difference relative to their standard parameter case. And the x-axis shows different cold ice activation energies. The different colors show a range of warm ice activation energies, and the different plots show different flow law exponents. So we can see in this figure that the amount of ice loss depends strongly on all three of these parameters. Zietz et al. Found that uncertainties in activation energy alone, within reasonable ranges found in literature, can account for a factor of 2 difference in ice loss estimates. So while this study is done with a grounded ice model and we're looking at floating ice shelves, it still emphasizes the importance of constraining these rheologic parameters. And constraining the parameters at ice shelf fronts could potentially have major implications for our predictions of ice flow-driven mass loss and sea level rise. So now we can get back to our experiment. We want to see which mechanisms and rheologic parameters more closely match the data from the Ross ice shelf front. So up until this point, I've been showing outputs from rectangular model geometries. However, in this section, I'll show results from a more realistically shaped model domain. We created a model geometry that thins increasingly towards the ice shelf front in order to qualitatively match the shape of the Ross front, which we derived from this radargram from the Rosetta Ice project. Here, we're again looking at this IceSat-2 lidar track from the Ross ice shelf front. We're going to compare our model outputs with the more realistic non-rectangular geometry to this data. So the blue line represents the model output with our standard parameters. Even after running the model for 5 years, the deflection amplitude reached only a few meters, compared to the almost 10 meters of deflection seen in the data. We therefore tried increasing the activation energy to 200 kilojoules and decreasing the average viscosity of the model from 10 to the 15 to 10 to the 14 Pascal seconds. This gave us a deflection amplitude that matched that of the data after just 7 months of bending, represented by the green line. The close fit of both the bending amplitude and wavelength to the data suggests that these parameters may be a closer fit to what is seen at the Ross front than our standard parameters. We also ran a model with these same rheologic parameters, but which incorporated a 20-meter wide submerged ice bench. The additional buoyant force from the ice bench allowed this model to reach the uplift amplitude of the data in just 2 months. However, this model had a much longer wavelength than what was observed in the data. So the short wavelength of bending at the Ross front suggests that the uplift observed there could be primarily due to an internal bending moment, as opposed to a bench. So this comparison serves as an interesting proof of concept, but a more rigorous comparison with data is going to require a more realistic model. I'm just going to take a quick. So among other simplifying assumptions, the models we've shown so far have used only one activation energy instead of representing it as piecewise with temperature. We also haven't incorporated a grain size dependence of the flow law exponent or the ice softness. And relatedly, we've only represented one viscous deformation mechanism at a time. So while these assumptions allowed us to simply validate the internal bending moment as the cause of ice shelf front uplift, we're limited in how robustly we can compare with the data. Furthermore, the parameters we've been using only correspond with substantial uplift at very cold surface temperatures. So we'd like to investigate whether a more complex rheology expands the parameter space in which we see upward bending. Our models have been relying on one viscous deformation mechanism at a time, but it's been found that multiple mechanisms allow ice to deform, with different mechanisms becoming dominant at different stresses and temperatures. At the stresses and temperatures found in natural glacier ice, the primary deformation mechanisms are grain boundary sliding and dislocation creep. So grain boundary sliding involves the relative movement of adjacent grains of ice at their boundaries. When grains elongate and change size under tensile stress, they leave gaps which other grains then slide into, resulting in deformation. This mechanism has been found in lab experiments to correspond with the flow law exponent of n equals 1.8. And the rate of grain boundary sliding is going to depend on the ice grain size, as larger grains will move past one another more slowly than smaller grains. And then dislocation creep is deformation that occurs within ice grains. This mechanism involves dislocations or line defects in the ice crystal lattice moving under an applied stress. Deformation occurs along basal planes via a series of small plastic strain steps that result in macroscopic flow. This mechanism corresponds with the flow law exponent of n equals 4 and does not depend on grain size. It therefore tends to dominate ice deformation at higher stresses and larger grain sizes. So not only do these mechanisms have different flow law exponents, but they correspond with different ice softness prefactors and activation energies as well. So in a study on the effect of grain size on ice rheology, Bain et al. 2021 combined experimental and ice core data to derive N, A naught, which they just call A, Q, and then M, the grain size exponent, for both of these deformation mechanisms. The parameters they found are all listed in this table. So note that for each mechanism, both A naught and Q have two values defined for warm and cold ice above and below negative 14 degrees Celsius. And then note also that the grain size exponent for dislocation creep is 0 because this mechanism is grain size independent. Grain size dependence is incorporated into Glen's flow law as shown in this equation. So we just multiplied the standard form of the flow law times the grain size d in meters of grain diameter raised to the power of the negative grain size exponent. So using these parameters, we can express two separate viscous flow laws, one for each mechanism. So while the models and analytic solutions we've discussed thus far only use one flow law throughout, a more accurate picture of ice flow includes at least 4 flow laws, representing these two mechanisms at both warm and cold temperatures. So even after isolating these deformation mechanisms, there's still uncertainty in identifying the exact values of these parameters. Goldby and Kolstad, in their very famous 2001 paper on ice rheology, found slightly different parameters, but we use the updated parameters from Bain et al. Because they combine results from several different laboratory experiments. But these values are by no means known for sure or set in stone. And then furthermore, the transition temperature between using the warm and the cold parameters is also uncertain and varies between studies. And then some studies find different transition temperatures for the different mechanisms, usually a higher transition temperature for dislocation creep than for grain boundary sliding. So on top of all of this uncertainty, without direct ice core observations, it's really difficult to model grain size variation with depth. So under low to moderate stresses, we expect the grain size to grow over time because larger grains reduce the total grain boundary area and are therefore energetically favorable. But at higher stresses, as dislocation creep dominates and dislocations accumulate inside the grains, it becomes favorable to nucleate new grains with fewer defects. Between the thermal drive for grain growth and stress-driven recrystallization. However, there's a lot more work to be done to constrain the parameters that describe the timescale over which these processes occur and how they respond to temperature and stress. So as an example, here are results from a grain size model from that same paper, Bain et al., representing steady-state grain size in a 1D column of ice with uniform temperature. So the first plot represents grain size with depth. We can see their models predict grain sizes ranging from roughly 100 millimeters in diameter at the surface to less than 1 millimeter at depth. And the red, blue, and green curves represent calculations using different lab and data-derived parameters. The subsequent plots show how velocity, strain rate, and effective flow law exponent vary with depth based on these different grain size results, plus the black dashed lines which assume uniform grain size. We can see that even small uncertainties in grain size propagate to large uncertainties in ice flow velocity, which is important for determining grounding line flux and ice mass loss. And even within a given set of parameters, we see factor of 2 differences in predicted velocities, represented by the blue and pink shading. And this is due only to uncertainty in the fit of the grain growth data to these parameters. And then we can also see how the effective n, the effective flow law exponent, varies really strongly on grain size, which we're going to talk a little more about now. So this effective flow law exponent arises from the way these two mechanisms are combined into a composite flow law. So the total strain rate is expressed as a sum of the strain rate due to grain boundary sliding and the strain rate due to dislocation creep. Using this composite flow law can add another layer of realism to our models, as in reality, both mechanisms are occurring simultaneously. When we expand this out, it looks like this. The strain rate is the sum of 2 independent mechanisms. And this is the fully expanded form of the equation. This form of the flow law with 2 different n values is more accurate than the simple n equals 3, which has long been used as the canonical value of the exponent in Glen's flow law. But the value of 3 arose because at the stresses and strain rates often used in laboratory experiments, the balance between grain boundary sliding and dislocation creep, with n values of 1.8 and 4, leads to an apparent or an effective flow law exponent of around 2.5 to 3. Okay, so now we can talk about how to incorporate grain boundary sliding and dislocation creep into our calculations. So to do this, for now, for the sake of simplicity, we chose to vary grain size between our calculations, but to use a uniform grain size with depth. We also still chose to use a linear temperature profile. We then guessed a strain rate for the ice shelf from which to base our stress calculations. So with the composite flow law, the driving stress cannot be found with the closed form solution, so we use Newton's method to find the driving stress at each depth. The driving stress depended on the chosen strain rate and the parameters for both warm and cold ice taken from Bain et al. From the driving stress distribution, we calculated the total longitudinal force and compared it to the force from water pressure to see how close we were to achieving horizontal force balance. We then iterated on the strain rate and repeated the stress and force calculations until horizontal force balance was achieved. We then calculated the total bending moment using the depth integral of the total horizontal force, and finally determined whether we expected uplift for the given grain size and surface temperature based on the size of this bending moment. So here are analytically derived driving stress distributions for the composite flow law. The y-axes show the elevation and temperature, and all cases shown here represent 300-meter thick ice shelves with cold surface temperatures of about negative 30 degrees Celsius, and linear temperature profiles that increase to 0 degrees Celsius at the base. So note that the driving stress is highest near the surface, where the ice is coldest and most viscous, as we would expect. The variation in driving stress with depth, shown on these plots, is what dictates the bending moment. So the first plot represents the simple single mechanism case with the uniform flow law exponent of n equals 3 and an activation energy of 120 kilojoules. For this case, instead of iterating on strain rate as in the composite cases, we set the strain rate at 10 to the minus 3 per year, based roughly off of the deformation rate of the Ross ice shelf front, and iterated on A naught until we achieved horizontal force balance. We can see that with these parameters, we expect uplift with a positive bending moment of 457 meganewtons. The rest of the plots represent cases with the composite flow law, which were determined by iterating on strain rate. The resulting strain rates are all reasonable, within the same order of magnitude as what we see on Ross. So notice these discontinuities a little halfway down the ice shelf front, a little over halfway down the ice shelf in each case, where we transition from the cold to the warm rheologic parameters. We see the largest stress variation, and therefore the highest bending moment, in the small grain size d equals 1 millimeter case, shown in blue. This case corresponds with a bending moment significantly higher than the simple case of 710 meganewtons. The 5 and 10 millimeter grain size cases also have positive bending moments, but the moment decreases with larger grain size. We found that the 5 millimeter case is roughly equivalent in bending moment to the single mechanism grain size independent case. And then we also calculated the stress distributions with the composite flow law for a warmer ice shelf with a surface temperature of negative 15 degrees Celsius. So in the simple case, we see that this warmer surface predicts a negative bending moment, as there's not enough variation in the stresses to produce uplift. However, in the composite cases, all three grain sizes result in positive bending moments. We can see that the temperature transition point is very close to the surface, so the majority of the shelf uses the warm temperature rheologic parameters, meaning that the Q, the activation energy value, is higher. We also see lower driving stresses near the center of the ice shelf and higher strain rates throughout, meaning more prevalence of grain boundary sliding, so a lower N value. Because viscosity, and therefore stress, vary with the ratio Q over N, we get a substantial stress variation even with less temperature variation. So this results in positive bending moments for all three grain sizes. The moments are small with the larger grain sizes, but are substantial with smaller grain sizes. It's encouraging to see that incorporating the more complex rheology could allow us to see uplift at ice shelves with a wider range of temperatures. And just to make this comparison more explicit, here we directly compare stress distributions with a negative 3 degrees Celsius surface and negative 15 degrees Celsius surface. The first plot shows the stresses for the single mechanism flow law. Note that the cold surface ice shelf has much wider stress variations and therefore results in a positive bending moment, while the warm surface ice shelf results in a negative bending moment. The second plot shows the stresses for the composite flow law with a 1 millimeter grain size. Note that the stress distributions are similar between the warm and cold cases, resulting in very similar bending moments of 713 and 710 meganewtons. And now, after exploring these analytic solutions, we tried incorporating the composite flow law into our fully two-dimensional models to see if we still saw ice front uplift beyond just the thin plate approximation. So these two-dimensional results are still somewhat preliminary, but we can glean some insights from them. Here we're looking at modeled surface profiles after 5 years. All of them bend upwards in moat rampart structures. The blue line represents the simple case with an activation energy of 120 kilojoules. The orange line represents a model that incorporated the composite flow law with a grain size of 1 millimeter. We can see that it exhibits more uplift in the same time than the simple case, and that using this composite flow law results in modeled uplift with a smaller wavelength than the simple single mechanism case. And then the green line also incorporates the composite flow law, but with a larger grain size of 5 millimeters and not as much uplift. So this shows us again that the amount of uplift depends strongly on the grain size. It should also be noted that these models see relatively little uplift of just a couple of meters, In the future, we'll further explore the parameter space to see if it's possible and reasonable to reach the deflection amplitude seen in the data with the composite flow law. And finally, here are modeled longitudinal deviatoric stresses for two simple models and two composite models. So the top row shows the results of simple models with a higher Q on the left and a lower Q on the right. As expected, there's more stress variation with depth when the activation energy is higher. The bottom row shows the results of the composite models with small grain size on the left and large grain size on the right. We can see that while the total difference between the maximum and minimum stress is actually larger in the simple cases, the stress gradient is more evenly distributed throughout the shelf in the composite cases, which we see results in comparable bending moments and uplift. So in conclusion, we've conducted the first two-dimensional models of ice shelf bending with depth-varying rheology. And with a simple single mechanism flow law, we've shown that our model results are consistent with the analytic prediction that ice shelves with a sufficiently cold surface and high activation energy will bend upwards. And we've also seen our models exhibit a shelf front bulge that causes uplift to outpace thin plate predictions. We also experimented with the composite or two mechanism flow law, and we found that incorporating grain boundary sliding and dislocation creep could lead to uplift of ice shelves with warmer surfaces. And we've seen that uplift with the composite flow law can exhibit a shorter wavelength than the simple case. We've shown how comparing model results with lidar data offers a way to constrain the mechanism of uplift, the rheologic parameters, and maybe eventually the grain size distribution. And looking forward, we'd like to do a more rigorous comparison of our model results with ICET2 lidar data, as well as expand on models with the composite flow law, and maybe including coupling with a grain size evolution model. And finally, if we're lucky, we'd like to take multi-beam sonar measurements of the fold-up shape of the Ross ice shelf front, which could help us determine the uplift mechanism and constrain these ever-important rheologic parameters. So thank you so much for your time, and I'm happy to take any questions.
Thanks a lot, Emily. It's great. Do you have any questions?
Hi, I had a couple of questions. If that's okay.
Yes. Yeah.
Hi, yeah. So I was totally unaware of this particular geometric thing before you started talking, so that's super interesting. Thanks. Is there a consequence of this kind of moat and rampart shape for the collection of surface meltwater or for blowing snow accumulation? I mean, is it? I mean, do you expect to see more pooling if an ice shelf was close to being, in a kind of collapsing state? Is that where you would expect to see the water piling up and perhaps helping fracture it?
Yeah, that's a really good question. And that's something that we have thought about but haven't quantitatively or rigorously looked into yet. But especially with the deeper moats that we see with the moment induced uplifts, it certainly seems likely that that would be a region where a lot of surface meltwater could accumulate and could lead to hydrofracture. So
Right.
yeah, in addition to the bending stresses, this could have consequences for surface hydrology and damage the ice shelves in that way as well.
I mean, does water infiltrating and then refreezing change the rheology outside of the parameters of your model, or is that kind of all kind of contained within a grain size distribution curve?
Yeah, I know that water and the ice does change kind of the ice softness and would impact the grain size and would just be another one of the many uncertainties that we would have to consider. But it's certainly
All right, interesting.
incorporated into some of these grain size models. Yeah.
Okay, cool. Well, I mean, was there any evidence that there was such a shape at the edge of Larsen B or any of the other ice shelves that have actually collapsed?
Huh. That's a good question. We don't have ISAT-2 data going back to when those ice shelves existed, but it would be cool to maybe look at. I don't know if even ISAT-1 goes back that far. I'm sure someone on this call knows. But that would be, I haven't encountered that in literature, so I don't think anyone has found evidence of that, but it's a good thing
You
to
could
look.
be the first.
I could be the first. Um,
Okay, thank you so much.
yeah, thank you.
One follow-up to Gavin's question, when you have the different shapes, would that also affect the way it fractures from the base? The
Totally, yeah.
different shapes.
The bench mechanism, it's been like codified very precisely where the location of maximum stress is expected to be relative to the front in kind of a thin plate model. And then it was cool that we saw those in the it was cool that we saw those in the two-dimensional model as well, that you can see this region of concentrated extensional stress at the base with the bench model. If we have uplift due to the internal moment, it kind of implies that it's because there's lower deviatoric stresses at the base and at the surface. So I assume we wouldn't expect it to be correlated with basal fracture in the same way we would the bench mechanism, which is another reason it's important to kind of disentangle the two.
Okay, Aaron has a question.
Sorry, I had to find the mute button. I'm not usually on my phone. Sorry about that. Really nice talk, Emily. I really think you're doing some neat work. The question that I have is kind of extending on what you've learned so far. The things that we don't know very well are, for example, the temperature profile of ice shelves are not typically like that. And there aren't very many measurements, but the ones that I've seen are not linear quite like that. So I guess I'm curious how that would affect what you can do and how much you feel like it's necessary that we collect those kind of data, or can we make enough assumptions and enough understanding to really use this information? And similarly, with the not just the crystal size, but the crystal anisotropy, that likely affects the stress distribution within ice shells too. So, and anisotropy is one of my favorite subjects, of course. So of course, I'm going to ask about anisotropy.
Yeah, I mean, more measurements are always better in my mind. Yeah, I know that the linear temperature profile is an approximation. My advisor, Roger, published a paper on kind of the analytics side of this and did numerical integration to look at kind of nonlinear, like Robin type temperature profiles or temperature profiles if there's more accretion at the surface or accumulation at the surface or accretion at the base. And oh, I'm going to get the direction wrong, but I believe it was more basal melt and more cold ice accreting accumulating at the surface ended up with a slightly higher bending moment than the linear temperature profile, and then vice versa if you had kind of melting at the surface. But there have been kind of borehole measurements on Ross that do show very linear temperature profiles, which is why we're like comfortable using it for like a first pass approximation at least. But I mean, yeah, if we could get more data of temperature profiles or grain size profiles, that would totally make these more realistic.
And anisotropy.
And that, yeah, I mean, that would play into the rheology in ways that I don't totally understand, but I know it would affect the flow law exponent, right? So yeah, that would be great.
Thanks.
Yeah, thank you.
Any other questions? Yes, I was also wondering about like spatially and temporally variable ocean temperatures, if that could have some effect.
Yeah, I mean, the warmer the surface ocean, the more likely we are to see the bench mechanism, because that's how the bench forms, is that the warm ocean kind of melts away the top of the ice shelf. But yeah, I think that's another reason that Ross is kind of so interesting, because it is in a colder region, but we do still see all of this uplift. Yeah, it would definitely affect it. I don't know. It would maybe affect the temperature profile at like the very ice front, the ocean temperature. But I don't know how far back that would propagate into the ice shelf.
Any other question? Well, if not, I guess we can stop there. So thanks again, Emily.
Thank you.
Thanks everyone for coming.